Hi, everybody. Welcome in. We're going to give a couple moments for all the attendees to load in. So please, while we're waiting, feel free to take a look at our reminders up on the screen, and we'll get started here in just a couple minutes.
So I hear the country is in a high alert for crazy weather.
Hi, everybody. Welcome in. We are waiting for people to load in. Please take a look at the slide as we come in, and just a couple moments, we'll get started. All right. I think we're just about full or getting to where we want to be with participants coming in. So I'll introduce quickly the slide that's currently up. Here are some upcoming events that we have through the CMAS Center, which is partnered with EPA and UNC. So please take a look with some of the links attached. We have ITM 2023 coming up in May, the 2023 International Conference on CMAS Asia Pacific coming up in July. And then we have just announced the official dates for the CMAS Conference 2023, sorry, 22nd Annual Conference for CMAS in October this year. As everybody comes in, a couple quick housekeeping reminders. Please be sure to post questions only in the Q&A, preferably not in the chat. Keeping it in the Q&A keeps it easier to track questions that have been answered or not. And also, if you have any questions, use the raise hand sign, or again, it probably is best to put all questions in through the Q&A, which you can find on the bottom of your Zoom screen. So now I'm going to pass it off to Sergey, who's going to introduce our presenters for today, and welcome to our CMAQ webinar series.
Thank you, Erin. Good afternoon, good morning, good evening to the audience here. Thanks for you all to join our resumed CMAS webinar series. I'm very pleased to introduce Dr. Sergey Napelenok and Dr. Ben Murphy from the US EPA. Both of them are no newbies to the CMAS community. They've been serving the CMAS community for many years, and most of us are familiar with them, but just to introduce their background, their expertise that they bring to the table. So the topic of today's webinar series is CMAQ version 5.4. That's the latest version of CMAQ that's been released, and then CMAQ's diagnostics, tools, and instrumented models. So we'll have a two-part presentation with Dr. Sergey Napelenok kicking it off, followed by Dr. Ben Murphy. Sergey has been with the US EPA since 2008. He's a research physical scientist with the Office of Research and Development. He has a BS in civil engineering, and an MS in civil engineering, and a PhD in environmental engineering from Georgia Tech. And his research interests includes the development, evaluation of photochemical air quality models, as well as their applications to study air pollutants for purposes of control strategy, health impacts, and climate interactions. He's been involved in a wide range of projects, including model sensitivity and uncertainty analysis. And what he is very well known for in the CMAS community is his development and support of the decoupled direct method in 3 dimensions, or DDM3D, and the integrated source proportion models in the CMAQ model. So that's Sergey. And then he'll be followed by Dr. Ben Murphy. Ben has been with the EPA since 2015. He's also a physical scientist with the Office of Research and Development at the EPA. And he has a BE in chemical engineering and a PhD in chemical engineering from Carnegie Mellon University. And what Ben does is he uses extensively and specialized experiences in atmospheric chemistry and physics, along with complementary computer programming experience, to contribute to the evaluation of more accurate, powerful, adaptable numerical models of the atmosphere for the benefit of public health and environmental pollution management. His specific research topics of interest are atmospheric sources, fate and transport of organic aerosols, and PFAS, or per and polyfluoroalkyl substances. He also leads focused efforts to improve the transparency and assure the quality of data products created by EPA's CMAQ model. with that, I think we're in for a treat, or a two-part treat by Sergey and Ben. And Sergey, it's all yours now.
Thank you, Saurav. That was a very kind introduction. Let me go ahead and bring up my stuff. Can just somebody confirm that I am showing a presentation?
Yeah,
please?
all good, Sergey.
Great, thank you. All right, so as you're probably aware, if you're in this audience, that we have released the CMAQ model version 5.4 a few months back. And you may have seen some presentations and seminars and maybe even one of these webinars on the different features and science updates in that release. So today we're going to expand on all that information and show you what we've done with some tools that came released with this version. And I'm going to talk about the integrated source apportionment method ISAM, and also the DDM3D, the decoupled direct method in 3 dimensions. And then Ben will follow with another presentation on the tools that he would like to share with you. So I'm going to figure out how to advance my slides. All right, so basically the best thing that I could present or to share with you today is to report on the fact that both of these models, DDM3D and ISAM, are finally fully integrated into the base CMAQ code. So when you go to download the CMAQ model package through GitHub on this link here, as you're used to doing for both code and documentation, you will find that both ISAM and DDM3D are included in the same repository as the base model. And just like in the past, both of these models can be enabled through some options in the building script. And they do not require any special scripts for both building and executing the models. They're just simply options within the existing default scripts that are provided. And still, you can configure and run both of these options through the run script, as I just mentioned, and they each have their own specific control file that you can configure and tell the model what it is you like to be doing. So I'm going to go through each one of these tools separately, briefly, just share a little bit of what we did to each tool and how it's been changed in the model. I'm going to focus mostly on CMAQ ISAM because that did undergo a substantial change in this new release. And then I'm just going to touch briefly on DDM3D because that one largely remained the same. So somebody just put up a question. I will say that I don't mind people asking questions, and we can certainly stop and answer them. If it looks like I'm running out of time, I will go ahead and stop taking questions. But somebody has asked, has there been any updates to CMAQ predictions for fires in 5.4? You're going to have to answer that yourself, honestly, and try and see what specific application you have in mind. But anyway, so CMAQ ISAM, as before, it provides source tracking information simultaneously with the concentration and deposition outputs. What that means is that as you're running the base model and you have enabled the CMAQ ISAM configuration, you can get the output for apportionment at the same time as you get for concentrations, and both for concentration fields and deposition fields, wet and dry deposition. And so this model has been released in CMAQ, but in parallel to CMAQ before, since version 5.02, and now it is released together with the CMAQ model, and it provides output as, for example, shown here on the panels on the right. So here I'm showing what might nitrate attribution to on-road emission sources would look like in the United States in an annual average. And you can see it kind of is concentrated on areas with high urban population density and lots of roadways, as you might expect. And then right below that, you see an example for an annual average of sulfate attribution from power plant emissions. And you can see high concentrations in the Ohio River Valley, as you would expect, but also additional individual power plants kind of popping out throughout the Southeast and some in the West as well, a little bit. So what this model does, as these examples show, is it tags specific tag classes such as sulfate, ozone, elemental carbon, and so on. And in the new release, what we've added now is the capability of tracking all CMAQ species that are available for every supported chemical mechanism. So now you get the full picture of, for example, PM 2.5, if that's what you wish, or all of the species if you really want to. And as before, it tracks emission streams as defined by the DECIDE model that was added also fairly recently to CMAQ, and it is available to be tracking online and offline sources. And you can subset these further by specifying geographical region also through the DECIDE module. So what have we done in the last update is we've kind of listened to some user feedback on the initial application of our ICEM model in the past and try to accommodate some applications that people essentially wanted to be doing with this tool. The tool is meant to be used by people for applications they want to be doing. So, and that is what we try to be accommodating for. So, and what we've done is better explained through an example. So ICEM tracks sources through various processes in the models. The kind of one of the more important ones, well, they're all important, but one of the more complicated ones is the chemical mechanism, which is a summary of all different reactions that you might be using to represent what's going on in the troposphere. And so here I have an example of a particular reaction that I just pulled out that would illustrate what I'm talking about. And this is coming from the CB6 chemical mechanism. What we have here in the black are two reactants. We have an isoprene product and also NO. And these two react to produce kind of a host of products with various stoichiometric ratios. And these are not exactly species per se, but they are kind of representations of chemical classes of species. That's why you have these weird stoichiometric numbers in front of them. And so the way we were doing this before is this: whenever CMAQ ICEM would hit this particular reaction, and I'm really oversimplifying this for illustration, is that it would look at what the source identity of the reactants was, and you get that because you knew what was emitting these. And then the products would be essentially inheriting the source identity of the reactants equally, right? So if in this reaction, for example, you're producing a bunch of NO2, and then when ICM goes and gets to this reaction and goes through the attribution process, it's going to say that NO2 produced from this reaction is going to be equally attributed to the sources of NO and the sources of this isoprene product, which what I'm calling here is kind of fair apportionment. And this was necessary because we wanted to design a tool that could be used for essentially any application that the users might have, because we're not sure what the people really want to be doing with our model. But it turns out that most of the stuff that people are doing with the CMAQ model is at least in the chemical mechanism world, is ozone chemistry. And when you do use this fair apportionment for ozone chemistry, it may produce some kind of non-intuitive answers. And what I mean here, I will illustrate again with the same reaction. So looking at the same reaction of this isoprene hybrid product reacting with NO, we get a bunch of stuff. As you might imagine, isoprene is typically biogenic in nature. It is emitted from biogenic sources, which are calculated either in line in the CMAQ model or specified by the user. And then conversely, NO is emitted mostly from anthropogenic emissions, such as EGU and mobile sources. There is a component of soil NO as well, but it's very small. And majority of NO coming into the CMAQ model, at least, is in fact anthropogenic. So if you look at this product and keeping in mind the source identity of the reactant, you will see that, for example, this NO2 that I talked about before is going to be produced and labeled or attributed half as biogenic and half as anthropogenic, because the reactants were half biogenic and half anthropogenic, which is fine, except and correct, except if you think about what happens next after this reaction happens. There are other reactions in the mechanism, and some of these cycle this NO2 back to NO in the process of producing ozone, for example, and other products. And so now you have this biogenically, or at least half biogenically NO2 quantity going back into the NO, keeping its biogenic identity. And when it gets this to hit this reaction again, it's going to slowly and surely or quickly, depending on your chemical conditions in the troposphere, keep pushing the products of reaction towards the biogenic identity. Because if you can imagine the cycling, and every time this occurs, more and more NO2 is being pushed towards the anthropogenic, towards the biogenic sources. And you can really see this in some applications. Here is a test domain we ran over the Chesapeake Bay area. And in this area, we have the Chesapeake Bay as a main feature. But out to the west, there are several sizable power plants. And when that were emitting essentially NOx. And then when we were tracking this NOx sources through this areas that also has high VOC emissions from sources around the Chesapeake Bay, we saw that there was some signature of biogenically labeled NOx in the plumes of power plants. It's kind of difficult to say. So, and that's essentially maybe considered a non-intuitive answer, because if you're emitting NOx from power plants, you expect that NOx to remain anthropogenic in nature because power plant is an anthropogenic source. But in fact, when this kind of cycling goes through the chemical mechanism, as I demonstrated earlier, you see that it can be relabeled into biogenic because of its interaction with VOC sources in the area. And some of that, this kind of behavior not only is non-intuitive, it's kind of difficult to explain to people and perhaps not wanted. So we've changed our model. We didn't change the model. We added new options to the model to be able to use the AESMD model more in an intuitive way for ozone applications. So instead of the one default fair apportionment method we had before, we've changed it to 5 options that you can set through the scripts. And option 1 is the same equal assignment as I've just explained previously, essentially the previous release of the model. But then we added this option 2, where you look at each reaction one by one, and you see what the reactants are included in that reaction. And if those reactants includes NOx or nitrogen containing species, and for CB6 mechanism, I have them listed here for an example, then whatever that reaction produces in the product side, all of those species, all of those products will be labeled will inherit the source attribution of the nitrogen containing sources only, and not the other reactants that might be present in the reaction. And then option 2 is the same thing, except we expanded the same thing as number 2. Sorry, option 3 is the same thing as option 2, except the list of species where assignment is performed is expanded to include reactive VOC species that participate in ozone chemistry. Essentially, all the reactive VOCs and their derivative radicals. And then from all of these options, if the reactants do not contain any of these special species, then the products are assigned with equal assignment, such as with option number 1. Then option 4 is essentially the opposite of option 2, where if you have a reaction that contains VOC species and the derivative radicals, then the assignment to sources will be done to those species only, and not to, for example, NOx sources. And then option 5 is probably what I'd recommend people use for in ozone kind of tracking applications. And this is done, this assigns assignment based on chemical ozone formation regime, and which is determined from the CEMM ratio from this 1995 publication. Essentially, you calculate the production of hydrogen peroxide ratioed with the production of nitric acid. And then you have this threshold value of 0.35. And then, on one side of that, it's in the NOx limiting regime. So if you encountered a cell in space and time that is NOx limited, then you will be doing the assignment, or the model will be doing the assignment and source identity and inheritance towards those NOx sources because it's not limited. And on the other side of the Stillman ratio, if it's a VOC limited regime, then the products will be assigned to the VOC sources. Now, there is some kind of newer research that's indicating that the Stillman ratio may be a little bit too high, and it could be low as 0.12, and there are some publications on that. And in order for people to be able to utilize those lower values, we made this value completely customizable. You can change that value in the run script and set it to whatever you want. If you don't like 0.35, you can use a lower one. That is not an issue. All right, so that's basically all we did for, for CMAQ-ISAM. A little bit briefly about CMAQ-DDM3D. What this model does, as it's been doing since version 4.7 in the CMAQ model, CMAQ world, and other models before it, is it provides sensitivities of the species fields, both concentrations and depositions. I think this is complementary information to CMAQ-ISAM, except instead of attribution, this is sensitivity. And this is sensitivity in the forward sense, in contrast to something like a CMAQ adjoint, which does them in the reverse sense. And that it calculates sensitivity of the full CMAQ modeling fields, sensitivities and concentrations and depositions to user-specified parameters. And these parameters can be things like emission streams, again, out of the DECIDE model. It can be things like initial conditions, boundary conditions. It can be chemical reaction rates. It can be things like the potential vorticity caused ozone incursion at the top of the troposphere. That's an option. And it propagates these sensitivity fields by differentiating the governing equation associated with providing the CMAQ solution to begin with in the same operator splitter kind of way as CMAQ does anyways. So here's an example of some of the studies we've done using CMAQ-DDM in the past on the left side of the screen. The first I'm showing you is the formaldehyde sensitivity to VOC emissions during one summer. And as you would expect, formaldehyde concentration is more sensitive to VOC emissions throughout the Southeast United States, because that is where higher emissions of VOC during the hot summer months occur. And then right below that, we have a time series at a site downtown Atlanta that's showing sensitivities to various emission sectors, sensitivity of ozone to various emission sectors that we were defining in that simulation. And here, this figure illustrates kind of one of the main differences between sensitivity and source apportionment. And that you will notice right away that some of these sensitivities are below zero, meaning that the sensitivity of ozone at this site during some days in July 2005 is actually negative, meaning that if you increase, for example, the blue one is mobile source NOx. So if you increased mobile source NOx incrementally in your domain, you will actually see a decrease in ozone concentration at this site. And that's also explained by simple ozone titration in the domain. So as I mentioned in the beginning, we didn't really do much scientific updates to CMAQ-DDM3D that at least the user will notice from their perspective, because the calculations are essentially done in the same way for both gaseous and particulate species as they were before. But there are some improvements for the users, from how the user interacts with the way they define the parameters that they want to track from the control file. I think that's done a little bit better and more intuitive, because more recently people want to track more things and more sources and more species. So the way that's done, I think is a little bit better. Kind of the biggest improvement, and it's probably more for me than anybody else, but it is important for the user as well, is that now when you do a CMAQ-DDM simulation, you have to provide the model with a Jacobian of the particular chemical mechanism you're using. And then whenever this mechanism would change in any way, it would often break the Jacobian, and that has to be recalculated. Now we've added the ability to calculate the Jacobian in line as the model is executing. So now you can go ahead and make changes to the mechanism within reason and still expect to have your model not to crash. Oops. So to summarize what I've talked about, and I'll open the floor for questions as well. As I've mentioned before, both CMAQ-ISAM and CMAQ-DDM3D provide, I think, useful and also complementary information for many different ways. You could look at CMAQ output. You can use it for just general better understanding of tropospheric chemistry. You can use it for control strategy, and it has been used for that. You can use it for propagating uncertainties, and we've done that as well, and many other kind of applications. And the fact that this model is now released within the CMAQ base model itself, it should be available to the user community more timely than in the past, where we would release CMAQ, and then there would be a lag of time, and then these other things would come out later. And also, we're still kind of working on some of the kinks with the release, and there will be the CMAQ version 5.4 plus that is coming out. Actually, I'm sorry, I don't know when exactly, but shortly, that will incorporate some more kind of updates that are minor and bug fixes in response to some of the experience the users have actually had on the CMAS hosted CMAQ forum, which actually appreciates seeing all the questions and feedback there as well. So that is the conclusion of my presentation. I see there's a question pop out. All right, so somebody is running CMAQ DDM. Maybe this is something we could talk offline on the forum. Right, in response to Mujtaba Sharif, I think this is something we could take offline for very specific questions like that and your specific experiences. There's a question, is there any improvements in time runs with new version of ISAM? We did have very substantial improvements of time or CPU usage for CMAQ-5.2, right? So if you've used a previous release of CMAQ-ISAM, which was like 5.02, or I can't remember exactly the number, that was taken very slow, and we took that user feedback seriously. And in 5.2, we had substantially increased the computational efficiency of the CMAQ model. All right, now we have, is there any improvements in, okay, that's what I just answered. Any more questions? Is there a max limit to the number of sensitivity parameters to be defined in the sensitivity file? There is not a max limit that I have run into yet. You are limited by the hardware availability that you have on your system, both in terms of how much memory you have available, because each sensitivity parameter essentially duplicates the memory requirement of the base CMAQ model. Also, on the same note, each sensitivity parameter outputs to disk the same amount of data that the CMAQ model does. So you have a limit on disk drive as well. And then you also have, how much you want to wait for your sensitivity to finish. But you can run very large sensitivities without an issue. The only thing I would suggest is that if the IO API library does have a limit on how many variables it could write to a file, but CMAS has released the large version of the IO API library, and I can't remember what the kind of the limit there is, but you could probably create even a larger one if you really want to. Okay. Is there any more questions? If not, I'm going to pass this to Ben. All right, Ben, take it away.
Right, thanks, Sergey. Go ahead and go in presentation mode. All right. And I'll ask for confirmation as well that I'm sharing the presentation and everyone can see it.
All good.
Great, thank you so much. And yeah, I thank you as well, Sarah, for the generous introduction at the beginning of the webinar. And thank you all for logging in. I scanned through the participants, all of your names, and it's great to be with some of you that I've worked with before. And I recognize a lot of names from publications with CMAQ, as well as a lot of you I've interacted with on the forum. So I'm really delighted to be able to share some time with you today. For this talk, I want to go through not necessarily the science aspects of a lot of the improvements that we've made for CMAQv5.4, but really focus on some of the tools and new features that we've brought in to make kind of common and routine tasks, as well as some kind of novel features or novel capabilities that we think will be useful to your work with CMAQ. Try to make these available into this newest version. There's 4 specific tools that I'll focus on. The Decide module, this new Elmo output module, AutoChem, and a new budget tool that we've introduced. And so I'll go through kind of the thinking, the kind of conceptual picture of each of these tools individually, and describe what features they bring in to hopefully save you some time and be able to get to your research faster. And then I'll go through some of the some kind of examples of using the interfaces for these various tools in some common tasks that you may want to do. And after each one, I'll kind of pause briefly to take some questions if there are any kind of pertinent questions to that specific tool that I just described, and then we'll kind of move on to the next. So the first tool that I want to talk about a little bit is the Decide module, or the Detailed Emission Scaling, Isolation, and Diagnostics module. We introduced this in CMAQ version 5.3. I think a lot of you are somewhat familiar with what it can do, and maybe even used it before, maybe even have struggled with it already since the release of that version. But the idea behind Decide is a relatively simple one to articulate. We're trying to centralize all the common emissions processing tasks into one kind of framework, one set of algorithms that will kind of unify the common things we need to do across all the different sources that CMAQ is considering. These include offline sources, mostly anthropogenic, which we can see here in the orange arrows. These are generally coming from the smoke emissions processing software, although it's kind of agnostic as to where these emissions come from, as long as they're in a file that's formatted for input into CMAQ as IO API format. There's also a number of emission sources that are calculated online within CMAQ. These are generally from natural sources, so windblown dust, biogenic VOCs, lightning NO, marine gas emissions, and sea spray aerosol. Now, in the past, before the Decide module was introduced, each of these online sources could be turned on and off, but in terms of chemical mapping, in terms of getting diagnostics for how the offline and online sources are kind of working together and contributing to the total emissions, these types of tests were kind of limited. And so the Decide module brings together these emissions into one centralized place in the code, and then adds some new features like bringing forward the chemical mapping to a user interface that makes it easy to make decisions about how components from these various emission sources will be mapped to CMAQ variables. We've also introduced the concept of using geographical regions within the CMAQ domain in order to set scaling parameters as a function of space. And then finally, what I'll describe a little bit more in detail during this talk are the improvements that we've made to some diagnostics, so that for any particular emission source, or for all emission sources, you can output what the emission rates were as a function of chemical species or groups of chemical species, so that you can have some more confidence that any kind of perturbations that you've made to your base module have actually taken place, Or you can also just get a record of what the base emissions were for a particular model simulation that you ran. So for version 5.4, to be specific in terms of what we've done with Decide, we've introduced the Megan biogenic VOC emissions processor as an alternative to the BICE emission processor, which has been available for since the beginning, my awareness is the beginning of the CMAQ versioning system. So now you have a choice between two different biogenic VOC models, BICE or Megan. Because of the capabilities of Decide, you can also run them together, and you can grab some chemical components from BICE and others from Megan if you have, some real deep knowledge about what you want for your biogenic VOC emissions and you want to have control at that level. We've also made we've also made updates to the diagnostic file system and algorithms. This includes updating the format of the files so that they are 100% consistent with input files that are read in that are output by smoke. So for example, emissions for gridded emission fields and point emission files tend to be in kind of 25-hour daily files. Those are now output exactly consistent by the Decide module. And so you can compare them one-to-one. There's no kind of interpolation across hours that needs to be accounted for. You can also sum multiple emission streams into one diagnostic file or keep them separate. And then there were some errors with our region scaling algorithms for versions 5.3, 3.1, 3.2, and 3.3 that we've now resolved in version 5.4. So that's something that you won't need to worry about. One other thing that we've changed that will become obvious from a user perspective is that we've split apart a lot of the user interface sections that were previously available in the emission control file into 3 different files. And this is to try to kind of decouple these options so that they can be controlled and kind of version controlled in a way that makes a little more sense. For example, all of the mechanism specific Decide scaling rules are now kept in a particular file, which is tied to each individual mechanism. But that allows for other user inputs that are more agnostic of what the individual mechanisms are to be tracked in other files, kind of separately and consistently. I'm going to go through just a few examples of the user interface that controls how diagnostic files can be formulated through Decide, and then I'll get to any of the questions that folks have submitted. So first, if you'd like to output one diagnostic file with all the emission rates from offline gridded and point sources, as well as online sources, all summed together, and you want to put this into one kind of 2D formatted file that is just a column sum across all of space, and you want to output this for all chemical species, then this is an example of the inputs that you would provide to this CMAQ control Decide name list file. There are 3 different fields that need to be populated. The first is to tell Decide what emission streams need to be considered. In this case, if you provide the total keyword, it will instruct Decide to sum all of those emission streams together into one value. Using the keyword call sum in this Decide diag format name list variable instructs the program to sum all of the layers across all space and provide one 2D output. And then finally, using this all keyword for the Decide diag species name list variable instructs the code to output information for all chemical species that are available on any and all of the emission streams that are available. To get a little more complicated, if you want to be provided with diagnostic output for only a couple of species instead of all the species that are available, you can use you can populate the fields in the same way. Only for the species field, you can select specific species like SO2, or in this case, I've chosen ASO4, which will instruct the code to sum together ASO4, I, J, and K, which is sulfate in the I, J, and K modes. So if you neglect the suffix for the mode for an aerosol species, it will sum all of them together. If you include the suffix, it will only output the information for that particular species in that particular aerosol mode. To get a little bit more complicated, if you want to output information about just a particular emission stream, in this case, point wildfires, then you can include the name of the emission stream from the CMAQ run script that you've used to name those emissions. So in this case, Decide will create a file that will be populated with wildfire emissions. I've used the keyword 3D for the second variable field here to instruct the code to create a file that has all 3D layers populated. And then for chemical species, I've selected CO and all elemental carbon that's in the I and J modes. So these are more relevant for wildfires, of course. But then you may want all fire emissions summed up together onto one file and not just wildfires. If you have, for example, 3 different fire sources that are going into CMAQ, let's say point wildfires, gridded residential wood combustion emissions, and prescribed fires from a point file, then you can put all of those together on one diagnostic file using a descriptor for the family of emission streams, which you may call fires. For this particular file, you can use a 3D format and the same chemical speciation that I showed for the previous slide. Now, if you want to define, you'll need to define this this kind of lumped descriptor for emissions, in this case fires, and you can do that in the same control file by providing the contents, the components of this fires emission stream family descriptor as the individual streams that you've defined on the CMAQ run script. And so these are provided in the same file, and you can kind of see those quickly as you're setting your inputs. Now, if you want to have those emissions for each of those fire sources separated out into separate files, you can also do that by setting 3 different sections of input for particular diagnostic files. But a shortcut would be to use that same kind of overall fires descriptor that you've already defined on the same file, and just include an asterisk at the end, which instructs Decide, in this case, to go ahead and split those out, populate the components of that descriptor, and create a separate file for each one of those, rather than summing them up together. So these 2 sections of user input would be synonymous with each other. So I'll go ahead and pause there. If anybody wants to submit questions, I'd be happy to entertain them, and I'll move on. So the first question I see is higher resolution 1x1 kilometer Beld 6 available now? So I am not qualified to answer that question, but I'll forward this to our expert, Jesse Bash, and he can provide an answer to that. Perhaps we'll do that over, perhaps we'll respond to the entire attendee list. I'm not exactly sure how, but we'll make that answer known to you. And then Joey Huang asks, when we define fires, in my case, even the point wildfires for 3D and residential wood combustion for 2D, they can still be grouped in the same group. Yes, so you can group 3D and 2D emission streams together. There's no problem doing that. That is a nuance that that I can address since you asked that, Joey. In this particular example on the right-hand side of the screen, if you were going to output a diagnostic for gridded residential wood combustion by itself, you would probably choose 2D here instead of 3D, and not waste a lot of grid cells at upper layers outputting 3D information. They would all be zeros. But of course, if you sum them together, then you'll get a 3D field that will be the sum of everything, even though gridded residential wood will just be in the surface layer there. So thank you for the question. And then the next question is, are there any differences between all and total? Yes. So in this version of CMAQ, we have now differentiated between keywords all and total when it comes to emission streams. If you use all, you will get each individual, you'll get a file for each individual stream separated. If you use total, they'll be summed together. So that is a nuance that we describe in the actual control file itself. So there'll be that definition for you as we've tried to define keywords in the past as well. And it will be defined in the, or it is defined in the CMAQ user guide as well. And thank you for the question. All right. So I'll move on now to another tool that we've introduced. This is the explicit and lumped CMAQ model output module, or ELMO. And I wanted to start with a graphical picture of what we're doing here, because I think that can communicate what we're trying to do very quickly. And then I'll move on to some of the more specific details in the subsequent slides. So on the top of this graphic, this is a picture of kind of the data flow from CMAQ version 5.3.3 and previous. And of course, from the model, we output a number of files, including the conc, aconc, pm-diag, and apm-diag. If you've used CMAQ before, you're familiar with these files. The conc and inconc files contain a kind of lowest level variables that are transported and reacted within CMAQ. Ozone, NO, and O2, various aerosol module species in the I, N, J, and K modes. In this case, ASO4 would be sulfate and ANO3 would be nitrate. On the APM-diag file and the PM-diag file, there are aerosol property variables, including standard deviations for each of the modes, diameters for each of the modes, as well as the fraction of each mode that is included in certain size cutoffs, like PM25, PM1, etc. There are some other variables that are present on that file as well. These variables can be put together using the combine tool along with species definition files that we have historically provided with CMAQ to create kind of aggregate metrics that you would commonly use for doing model ops comparisons or understanding how the model is performing kind of holistically. These can include total PM2.5 mass, total organic matter in the I and J modes, and so on and so forth. We are taking the speciation part of this combined calculation or combined post-processing task, and we're putting it online within CMAQ now. So ELMO is doing all of this kind of speciation aggregation online based on particular variables that you, the user, would request. So files for AELMO, which would be averaging across the hour, or ELMO, which would be instantaneous on the hour, contain variables that you decide that you may want, including total PM2.5 mass, total PM10 mass, fine particulate matter mass, fine PM mass of just sulfate, of just nitrates, of speciated fine PM mass, as well as meteorological variables and others. I'll show an exhaustive list in a couple of slides. It's still useful to have combined to be able to concatenate daily output together into monthly files. But in terms of speciation and creating these kind of aggregate variables, that's all being done now within CMAQ. And it's done across all mechanisms. You no longer have to understand which chemical species go into SOA depending on what mechanism you use, for example. The model can give you SOA mass regardless of what your underlying chemical description is. So here are some specifics about this new ELMO system. It's, as I've described, online processing of aggregate variables. It can also write out conc and aconc variables to this ELMO and AELMO file. So you can put those together. You can put PM2.5 and ozone together on the same file. It's available for instantaneous and average daily files with hourly resolution. You can choose 2D and 3D formats. And you can make up your own variables and add them to the system. That's not exactly turnkey, like you wouldn't be able to do it from a user input file, but it's, I think, made more transparent and centralized within the code so that you can modify source code relatively easily, compile, and then get your own new diagnostic variables that you'd like to use for your own purposes. If you want to add your own variables, please just reach out if you get stuck, and we'd be happy to help you get through that process. In the future, we'll be making ELMO available for other instrumented models, including AESMD, where it would be useful to have lots of data processed online and then output directly for your own purposes. Okay. So here is a list of species that are available from the ELMO system that you can ask for using the interface. As I said before, lots of different ways of representing aerosol mass, different size regimes are available, as well as speciation for example, PM2.5. You can also get speciation for other types of PM cutoffs, including PM 1.0, as well as aerosol mass spectrometer relevant speciations. This is kind of using a projection for the AMS in order to calculate that. You can also get the speciation as a function of kind of total fine particulate or coarse particulate. This is summing together the I and J modes or the K mode, respectively. You can still output aerosol properties to these ELMO files, aerosol number metrics, other variables that are pertinent for aerosols, including AOD, the reaction rates for various heterogeneous aerosol processes, and toxics are available, as well as meteorological variables. So all of these are available for outputs in ELMO files. It puts it in one place for you to be able to then use to further post-process and suit your needs. And yes, as I said, you can of course output all raw gas and particle species as well. So ozone, toluene, you name it. Here are some examples of the interface for ELMO. Tried to streamline it and make it as easy as possible. There are variables for setting the average layer top and layer bottom, so you can just output the surface or all vertical layers or anything in between. And you can choose your speciation. So here's a very simple example where you only want kind of NOx variables, ozone, and PM2.5. And you don't want to output every single ELMO variable that there is. You want to save storage space and reduce the size of those intermediate files. You can populate the chemical species list with just NO2, NO, ozone, and PM2.5, and ELMO will give you those values. If you define NOx as a chemical family, using the CMAQ miscellaneous control file, then you can use NOx directly and reduce the number of chemical species from 4 to 3 even further. So if you're limited in storage space on your server, or you're using a cloud deployment and you want to reduce the amount of storage space that these files are taking up, then this can be, I think, a useful option. If, however, you want to look at all fine mode species for aerosols, but you don't remember which ones are available, sulfate, nitrate, ammonium, and organics, but you forget what other ones CMAQ may have available, you can use a keyword like fine species, and ELMO will automatically populate all of the fine mode species that it's aware of, and it will give you all of those on your output file, and you don't have to know them specifically. It also, makes it a little more human readable to look at this variable list. In this case, it's outputting also the PM2.5 mass, as well as isoprene and OH radical concentrations as an example. So this can create a nice kind of condensed list that is then expanded out in terms of what you'll get on the output file. If you're using the AMET system, the model evaluation tool developed within ORD here, then there's a number of variables that are available by default for model obs comparison in that system. It includes, of course, ozone, I think NO2, and then a lot of the aerosol speciated variables. If you use the AMET keyword, it will make sure to give you all of the variables that CMAQ knows about that can be used in the evaluation process of AMET without you having to know what those variables are. You can also use the SAT keyword to get a list of variables, both on the meteorology and chemical side, that are useful for doing a satellite comparison. This includes the air density, cloud fraction, potential vorticity, pressure, temperature, chemical variables that are commonly available from satellite retrievals. Those will be directly output for you. In this case, I've put the top and bottom for the field as the first layer. And if you use the satellite keyword, presumably you'll want all the layers available to you if you're wanting to do something that's that has some kind of layer aware analysis to it compared with satellite retrieval. So keep that in mind. But if you're just wanting to compare with AOD, for example, across all of space, then choosing one layer would be fine. You don't need to have it vertically resolved. If, however, you are a little bit anxious about using, the new Elmo speciation interface, and you just want to have everything that CMAQ5.4 was giving you after running through the combine tool using the SpecDef, the speciation definition files that are provided with the code, then you can just use this default keyword, and it will dump the whole host of variables that were available in that method. So you get a pretty large file, but it should be pretty exhaustive and support anything that you were doing in terms of post-processing with CMAQ5.4 or before. All right, so I'm going to pause here and take questions if there are some. Is there any limit for number of variables in the name list? I don't think so. I might have put an arbitrary limit at 1,000 or something like that. But the way that the name list is processed, it reads in the value for that list and then seeks to find the end of the list wherever it is. So, there's an arbitrary upper limit that can be changed in the source code if you happen to hit it. If you run into what looks like an upper limit, then send reach out to us over the CMS forum, and we'd be happy to track down and see if that's the issue. But you can definitely output. So, for example, rather than using the default keyword here, if you put all, then it will give you everything I've gone over on these slides, as well as every single raw, gas and aerosol species on one file. And it's enormous, but it's possible. So where can I find a list of the ABRG, VARs, and ML, and can I make my own list as well? At the end of this presentation, I will show you, there'll be some links to the user guide. And I think in the appendix of the user guide, there's a table of all of the average variables that we define and what their contents are. And those, of course, can be changed. They're all defined in the source code. You can look them up. In terms of the name list itself, the default name list is kept intentionally quite brief. It's actually consistent with the example I'm showing here. But if you have a need for a specific type of output, and you want to reach out and see if that's been done before, or if we have any recommendations, be fine to reach out over the CMS forum if the user guide isn't fitting your needs. Okay. I'll move on now to the next tool I'd like to discuss, which is AutoChem. So here we want to support the capability to be able to make easy, small changes to the chemical species within CMAQ, as well as the chemical reactions or reaction rates that are being fed into the chemical mechanism. If there should be changes being made to the species or to the chemical mechanism, we want to be able to support users to making the source code that CMAQ needs to drive those changes in as easy a way as possible. And so, for example, in CMAQ version 5.3, if you made any changes, in CMAQ version 5.3 and 5.4, if you have the CMAQ repo on your local system and you use the build it CCTM CSH script, then it will automatically copy out all the necessary source code files from the repo directories to this kind of build directory. And then any changes that you make to the files that are kind of corralled in these red dots here will need to be propagated over to source code files, including reactions data.f, reactions func.f, and these solver files as well. But making these changes manually is not recommended. So Bill Hetzel on our development team created a number of utilities that will actually generate the source code files from any changes that are made to the chemical species name list or the mechanism definition file. And so these utilities can be used. He has really detailed and helpful documentation within the CMAQ repo that will use these utilities to create the source code files you'll need to drive CMAQ. However, we've also added this buildit mech.c shell script, which is fired off by the buildit CCTM script if you want to automatically run through all of these utilities without running them manually yourself. So that is what we're calling AutoChem. In other words, if you make any changes to these name lists or to the mechanism definition file and you uncomment this line in the buildit CCTM script, set build mech, then the buildit CCTM script will know to run buildit mech using all of the options that are populated in the buildit CCTM script to drive these utilities and create the source code files for you that you don't have to do them yourself. By default, this script will also try to pass back the source code files that you have created in this process back into the repository. If you already have a mechanism that is in the repository of the same name as the one that you're trying to create, then you'll get an error from this script saying, I don't think you want to overwrite your existing mechanism with these new files. That's to prevent myself, other developers, and users from overwriting default mechanisms like CB6 version 5 with something that is maybe an experimental mechanism. We don't want to necessarily overwrite the default. If, however, you do want to overwrite the mechanism in the repository, you can uncomment this set clobber mech option, environment variable, and the script will then overwrite anything in the repository matching that definition. Okay. Just one note to folks who are using this tool, that if you're adding aerosol species to your chemical mechanism that don't exist already, there's some other places in the code that need to be modified, including the aero data registry table and the SOA DEFIN registry table. These are in the aerosol name list. They're in the aerosol module. You also need to modify the Henry's Law coefficient parameters inside the cloud module, and then the CMAQ control stage name list. If you're using the stage module for deposition, you need to add some parameters there as well. So these slides will be sent out to everyone so that you can keep these in mind as places where updates should be made. And again, if you're having trouble adding aerosols to your configuration of CMAQ, please reach out over the CMAS forum. We'd be glad to help. Okay. I'll go ahead and pause here, see if there's any questions. I'm not seeing any already. Okay, I'll go ahead and move on to the final tool that I wanted to discuss. This is what we're calling the budget tool. And I think this is also perhaps pretty easy to describe, at least in concept. And that's what we want to provide is a very simple human readable ASCII text file output from a default run of CMAQ that will tell you, as a function of chemical species, what the overall burden is in the domain, as well as what the rate of mass addition or destruction is for every chemical process. In other words, the mass balance of every chemical species that CMAQ is calculating domain-wide. So this tool will by default create a text-based output file called CCTM budget. So it's going to provide values for you in terms of kilograms and kilograms per hour for every single model chemical species if you choose. You can also ask for sums of species. If you define those as chemical families, you can refer to them. I'll show some examples of that on subsequent slides. And here's a list of all of the processes that are tabulated for this budget tool output. So there's transport processes like vertical diffusion and advection, horizontal diffusion, as well as advection both in and out of the domain on all of the faces. In this case, a rectangular domain that would be used compatible with like a WRF style meteorological simulation. There's also non-transport processes, of course, like emissions, dry deposition, cloud chemistry and scavenging, gas phase chemistry, condensation and coagulation, new particle formation, and then growth from one aerosol mode to another. These can all be tabulated, or these all are tabulated in the budget tool, and you can then parse them with your own codes to analyze the total generation and destruction of compounds. There's also a residual component that is output to give you some idea of the overall, how well the overall mass balance is working. So if this residual component is rather large compared to the other processes, it tells you that something is being unaccounted for in the model. So this can be very powerful for perhaps diagnosing bugs if you're making lower level changes or introductions to processes within CMAQ. Here's an example of parsing some of the budget tool output information and then using it to verify that no large scale changes have been made when a model change has been introduced. So you can see output for various processes going along the y-axis here. The x-axis is kilograms per year in log scale. So to the right of the 0 is generation of mass, to the left is destruction of mass. I'm summing together a lot of transport processes here. So this is total diffusion in both directions, and then total x advection and y advection on the second and third rows. And these values are summed for all SOA species in a base simulation, and that's on the top row of every single pair of data here. And then in another simulation where I've made a change to the way SOA was classified in terms of being wet aerosol. And so what I'm showing here is that if we stratify the data by day and night and look across all the different processes, we don't really see any large scale changes in the total domain-wide processing of SOA. You can look at this, on a per species basis, and it can be really helpful for seeing how mass is flowing through various chemical systems. So that's available now for your use. Here's some examples of the interface for this budget tool. Again, quite simplistic. We've tried to keep it purposefully very simple. You can turn the tool on and off using this true false variable in the CMAQ control miscellaneous name list. You can also set all of the variables that you want to output. If you use the all keyword here, it's not going to be all in terms of the Elmo species that I showed you before. This is really just all of the CMAQ transported and chemically reacted species. Everything from ozone and hydroxyl radical up through sea spray cations, for example, and aerosol sulfate in each of the 3 modes. You can be more specific, of course, and just specify that you want to output ozone, NO2, and elemental carbon in the J aerosol mode, for example. Or you can use definitions of chemical species in order to simplify the output from this budget tool. So for example, you can specify ozone and NO2 as lower level species. You can then use elemental carbon as a bulk aerosol. Don't need to define that one as a chemical species because CMAQ automatically knows that if you omit the suffix of the aerosol species, it will go ahead and sum across all modes. But if you want to use a term like VOC, you will need to define that as a chemical family. And this is because it changes by definition based on the chemical mechanism that you use. And we think there's enough variability in the way that users would define VOC depending on the particular measurements that they're comparing to or the particular purposes that they have in mind, that we didn't really want to provide a blanket definition of VOC on our side. That's something we might reconsider in the future, having a default definition for VOC. But at this point, if you want to use VOC as an overarching term, you need to define it yourself as a chemical family, which is done in the same file here. Okay, so I'll go ahead and summarize and then take any final questions. I went over 4 different tools that we've either introduced new in CMAQ version 5.4 or made updates to. These include the Decide module, Elmo, AutoChem, and the budget tool. We're really trying to focus here on user needs and ways of streamlining the tasks that you're doing all the time. And when we can, speeding up model calculations and reducing the amount of time you're spending on post-processing or the amount of storage space that you need for post-processing. Here's a list of links that you can use to get information about these various tools. All of these go to various parts of the user guide that we've provided along with the public release of CMAQ version 5.4. So some of them are going to the appendices of the user guide, some of them are going to specific tutorials. And then of course, there's a link here to the CMAS forum which we encourage all of you to use to reach out to us. Hopefully we can help you with any more difficult problems. So thank you again to Sarav and Aaron for facilitating this meeting, inviting us to come and present. And I'd be happy to take any questions that you have. Thanks.
I don't see any questions so far, Ben. I think whatever came through have been answered. We'll maybe pause for a few more seconds, see if anyone is still thinking. Oh, there's one.
There's one. Can we get output of all layers other than average of layer top and bottom by using Elmo? Yes. So to be more clear, when outputting Elmo files, the average, the A Elmo that I showed, the average Elmo is an average in time. So you're getting an average across an entire hour rather than an instantaneous value at the hour for every hour of the day. That's the averaging that's done in Elmo. There is no spatial averaging done in Elmo. So if you extend out the layer top and layer bottom in those Elmo options, it's going to provide you with a 3D file of that size, not an average across all of those layers. So, just as an easy example, if you provide the bottom is layer 1 and the top is layer 34 in a 34 layer simulation, then you're going to get every single layer output from Elmo directly.
While we pause for any other questions, I just want to add that to an earlier question on the number of variables in the name list. I just added a written response to that question to point people to IO API 3.2 large, which supports a lot more variables than the standard default version. So if you use the default version, you have a limit of, I believe, 2048, and the 3.2 large allows you to go 8 times larger in terms of total number of variables. So please watch out for using the large version if you're having applications that require more variables than 2048.
Yeah, great suggestion. Thank you. Yeah, especially important for ISAM and DD, anything source resolved, of course.
Yeah.
Right.
Okay, I don't see any more questions. Thank you, Ben and Sergey. I think there were two very, very informative presentations. Talking of Elmo, I know Elmo helps kids a lot. I didn't realize Elmo can also assist scientists. I thought that was very nice. Thanks to both of you for talking about these various tools. If there are no more questions, I think we can sign off. I do have, let's take a moment to acknowledge and thank both Sergey and Ben for a nice presentation. Thank you, Ben, Sergey. I do want to make one more announcement besides the ones that Erin made at the top of the hour, which was the 3 upcoming CMAS conferences, or supported by CMAS partly, the ITM in May, the CMAS Asia Pacific in July, and then the CMAS Chapel Conference in October. I want to make an open invitation to all attendees on this call to also see if you have any particular new update or an application which is of interest to the broader CMAS community, to reach out to cmas@unc.edu with a proposed topic that you would like to present to the CMAS community through these webinar series. We want to revive them. And again, thanks to Ben and Sergey for kicking off this revived series this year with their first talk. And we'll hopefully have a few more this year. If you have an idea or a proposal, please reach out to cmas@unc.edu. With that, thank you all again. I believe Erin will post the recording of this talk for future access on the CMAS Center website. Okay, thank you and have a great day.
Thanks a lot.